Welcome back to the lecture hall. Hope everyone has recovered from yesterday's bar night. This morning we have the final part of two tutorials, and we start with the third lecture on invariant and quasi-invariant measures for actions of oligomorphic groups.
Okay, so thank you very much. Well, thanks to everyone who woke up and is still here. Okay, so I had this invariant and quasi-invariant measures in the title, so maybe now is the time to talk about quasi-invariant measures. And okay, so maybe I'll remind you what the thing is. So who's called them? Let's see, measure class preserving actions. Okay, so maybe I'll keep the same terminology. Good terminology. So measure class. So sometimes they're called things like quasi-measure preserving. So this is another word which is used. Or also non-singular actions. Okay, so all of these things mean the same thing. So it is an action of a group which acts, say, probability space. But now you don't you don't insist that the measure is preserved. What you insist is that the idea of null sets is preserved. Right? So this means that one way to say this is that if you take every G in G, when you push forward the measure mu by G, you get a measure which is equivalent. Okay, so this is, as I said, so it's the same as saying that the null ideal okay, so remember there was this notion of this measure algebra, which was just the quotient of this B by the null ideal. So because the ideal is preserved, and of course the algebraic structure is preserved, so you do get an action on the measure algebra. Okay, so this does descend to an action on the. But now, of course, so this is still an action which is by isomorphism, but it is not isometric. Right, because the measure is not preserved, so maybe you have a set of measure 1/2 and you send it to a set of measure 2/3, and this is enough. Okay. So it's basically an action which just preserves the algebra structure. Okay. But somehow, despite of this, you get unitary representation, because if you remember, so sort of the main theme of the whole thing was how to use unitary representations to prove results about ergodic theory or measure preserving actions. So you still get measure preserving actions or using the still get unitary representation using the random equilibrium derivative. So so if you have a measure mu which is absolutely continuous with respect to mu, right? So this means that every mu null set is mu null. Then, well, there is, so the random equilibrium derivative, so it is a function, which is denoted like this. Okay, so this is the function in L1 of mu. Okay, and it has, well, so the whole property of this thing is that, so when you integrate the function f with respect to mu, is the same thing as integrating f times this derivative. And of course, this is somehow how this notation came up, because now you can cancel this. Okay, and you also have, so when the two measures are equivalent, right? So this just means that, I mean, you have this relation in both senses. So this means that, so if mu is equivalent to mu, well, then this function is, of course, it is positive. Yeah? So it's an L1 function which is non-negative, and when the measures are equivalent, the function is actually everywhere positive. I mean, this is the same thing, and then of course you have this this thing that the mu times. So this is sort of a basic measure. Right, and also how do you use this thing to produce a unitary representation? So I'll just write the formula. Okay, so So I have an action here, and I want to produce an action on L2. So L2 of x. So it is done. Well, you do it in the following way. So you start with the function f here. Yes.
Is it almost everywhere or everywhere?
Well, it's almost everywhere, sure. I mean, the idea is that, yeah. I mean, everything is up to. I mean, this is an L1 function. I mean, my idea is that, so yes, the place where it takes value 0 has measure 0.
You can make it 1/3. You can make it 1/3 to work.
Okay.
I'm saying that wherever it's 0, you can change it to be 1 instead.
That's true. I can, yeah. Okay, so let's continue. So we get an action on the Hilbert space. So here's the formula. So if you have G, you want to act on a function f, and you want to evaluate this at x. So what you do is you take, so you take the Radon-Nikodym derivative of, so you push forward the measure mu by G. You take a measure which is, you get the measure which is equivalent to mu. You calculate its Radon-Nikodym derivative with respect to mu. Like to power 1/2, and then you just shift. So of course, if the measure is invariant, this measure is invariant just means that this Radon-Nikodym derivative is just always equal to 1. Okay, then this term does not appear, and then you just get the normal shift. But if the measure is not invariant, I mean, you correct by this term, which makes, I mean, when you write down the formulas, you observe that this preserves the norm and the inner product. So the reason this 1/2 appears here is that the Radon-Nikodym derivative is in L1, and here you're in L2. So to get from an L1 function to get an L2 function, you put 1/2. So this is the right. And so this is well, it is a unitary representation. So it's action by unitary isometries on the Hilbert space, and moreover, so it preserves more structure. Okay, so not only does it preserve the Hilbert space structure, but it preserves the ordering. Right. So this is a space like this L2 of x. So it's of course the Hilbert space, but it also has additional structure, which is it's an ordered vector space. And this action, of course, is preserved. Yeah. So if you have a positive function, also sent to a positive function. Okay. And so this is well, this thing with the ordering is what is known as a Banach lattice. So not only is it an ordered vector space, but it also has lattice operations. Right. So you have F1. F2 is, well, I don't know, it's the pointwise maximum. I'm not sure how to. Okay, so it's the pointwise maximum of the two functions, F1 and F2. So this is a lattice, right? So you have also the minimum and so on. And so, of course, these operations, because they're defined in terms of the order, they're also preserved. Okay, and so conversely, maybe I should write this down. So conversely, any unitary operator on L2 of x, which preserves the order, arises from yes, thank you. Arises from a measure class preserving. So this is, I mean, if you just, so you can just forget this measure algebra and so on, just look at actions on F2. And so as long as you preserve the order, you are like this. Okay. And so one more important thing. So you see this, I mean, when you have a function f, really not a lot is preserved, but at least there is something which is the support of the function. So the support of f, it is some functional analysis. Yes, I mean it's not very hard. So if in addition you preserve, okay, so maybe I should say this. So if in addition to the ordering you also preserve the function 1, then you're automatically measure preserving. So this is somehow how you distinguish the groups inside the unitary group, right? If you have the order. I mean, it's so you see actually how you get this right away. So the support, of phi, you define this to be just the set of OX's. X is the f of it 0. And what you observe is that, I mean, if you preserve all of these operations, you preserve supports, and once you preserve supports, then you get an action here. Because somehow orthogonality tells you two functions are orthogonal. I'll write this down because I will use it. So if you have f1 and f2, so f1 and f2 are positive functions. So F1 is orthogonal to F2 in the Hilbert space setting if and only if they have disjoint supports. And once you have this, it's very easy to recover the action of the measure space. All right, so was there anything else, like part of the general thing I wanted to say? This is probably about it. Okay, so there is another very basic lemma, which I will write here about these things. So again, so if you have a measure class preserving action like this, so preserving, then the following are equivalent. One is that so the action on L2 has a fixed point. Fixed vector, or non-zero, of course. Yeah? And two is there exists a measure mu, which is absolutely continuous with respect to mu, which is actually G-invariant. Probability measure. Well, there is, there's nothing to this, yeah. So what is the? So say one from 1 to 2. If you have some, if f0 is fixed, then the absolute value of f0, which is equal to the maximum of f0 and minus f0. So this is also fixed. Because remember, my action is preserved for this operation. So if I fix this point, I fix also. I fix this, and now this is a positive function, and I can just define mu to be, I can just define the Radon-Nikodym derivative of this to just be the square. Okay, so this is an L1 function. It defines a measure, and this function is fixed because the function is fixed, so the measure is fixed. And well, you can imagine that the opposite direction works exactly the same way. So
we want to renormalize with probability measurements.
Yeah, I probably want to renormalize it. So I want to take the f0 to be of norm.
It's a finite positive measure.
Yeah, it's a finite, so it doesn't matter. You're right, I have to renormalize. And then the other direction works exactly the same. All right, so where is so far so good? Good. All right.
The other direction, the derivative is fixed.
Yes, if the measure is fixed, then the derivative is fixed, and then this gives you a fixed point. Again, you have to do this one half business to go from L1 to L2. So this actually doesn't matter. Somehow the whole theory works for all of the LPs. You just have to put the correct. I think that these lattices, okay, they're not isomorphic really, but if you put LP instead of L2, so say in continuous logic, all of these things are bi-interpretable. So they're basically the same object. They have the same automorphism. So,
interdefinable. Interdefinable, not just by.
Yeah, interdefinable, yes. And you just use this, this P1 over P all the time. All right, so so one more piece of terminology. So an action, so measure class preserving action. So it's of type 2-1. This terminology comes from Fallman algebra, so I really don't get into this, but this is how they're called. If there is a probability measure, if there is a probability measure mu, which is invariant, so mu which is equivalent to mu, invariant. This just means that it is actually a PMP action. Okay, up to changing the measure, but you know, you can always change the measure. It doesn't matter, and then so it's the same as a PMP. And so you say it's of type 2 infinity if there is a so the same thing, except that now it is not a probability; it is an infinite for sigma finite. Which is invariant, and then it is of type 3 otherwise, which I really so I don't want to. I mean, it's a bit of a silly classification, right? You have the two type, and then you have the third type, which is not the other two. But there is actually some theory about type 3, so it isn't completely. So, for example, the action that so Anush considered from on the free group on the set of ends, it is a type 3 because it does not preserve neither finite nor. I should also say so. These you see, I started so my mu in the beginning was a probability measure. But it doesn't really matter. So the thing is that once I only care about the measure class, so the null ideal, I could as well have started with the sigma finite measure, right? Because every sigma finite measure is equivalent to a probability measure, right? You just cut the space into infinitely many pieces, and then you normalize by 1 over 2 to the n each piece to get from an infinite measure to get.
If you don't have sigma finite, it'll have random negative, right?
Yeah, so it has to be sigma finite. This is otherwise the whole theory just breaks apart, and it's not. I mean, it is about sigma finite. Okay, so now what I want to do. Okay, so there's one more. So there's a way to construct actually actions like this. Okay, so maybe there's one obvious one for our say. Remember we were interested in these permutation groups. So of course, if I have a permutation action. Of course, this is an action of type 2 infinity, right? Just because it's a countable set together with the counting measure. So the counting measure is most certainly preserved. So this is an action of this type. And there is a sort of slightly more general construction that you can do. So it's called induction. Okay, so here, so induction. So it's a construction. So it has an input. So you start with group G. If you want, it's an arbitrary topological group, and you have an open subgroup V. Okay, so V is an open subgroup. Maybe it's not so arbitrary because for it to be interesting, you need to have like a lot of open subgroups. So it's basically for non-Archimedean groups. Okay, and you also start. So another thing that you start with is. So maybe should I put Z mu. So this is a PMP action. So this is a probability measure preserving action of the small one.
What's that?
A PMP, a probability measure preserving.
Okay.
Just something. Okay, and then so this is the input, and then the output is a to infinity action of G. Okay. So what is the space? So this is so it's a procedure which produces an action on this space. So it is G mod V times Z. Of course, with the measure is the counting measure here times the probability measure here. And this measure will be preserved. So how do you obtain it? So I'll draw a picture and then I'll write the formulas. So what you do is you just this space. I mean, this is just copies of Z, which are indexed by the cosets of V in G. And how does the action work? I mean, so the V, so say maybe this is the first copy, which is indexed by the coset V. So the action here of V, of course, is the action that, the action that you started with, right? And then if you have now a G which sends this coset to this coset, well, you imagine that, so you send this piece to this piece, right? So if this is GV, when you act with G here, it just sends it here. And then you make it in such a way that this thing is actually compatible and defines an action. Okay, so I'll write the formulas right away, but this is sort of the type of picture to have in mind. Okay, so let me actually make this precise.
So some sort of a Mackey construction.
Yes. I mean, it's induction. So okay. I'm not sure what the oldest. So this thing appeared in representation theory really long time ago. I think it's Frobenius. And then, of course, it was copied in all sorts of things. There's also this construction of co-induction, which is very similar, but it produces a measure. I mean, starts with a PMP action and produces a PMP action. But then you have to take products instead. I mean, it's a little bit different, but it's the same thing. I mean, some sort of a joint functor to something else. Okay. It has some categorical categorical interpretation. Okay, so let me write down the formulas. Correct. So what do? These formulas are easy to get wrong. So you start with a section. So you start S. So you just pick a section from G mod V into G. So what is a section? I mean, just means that, so of course you have the quotient map from G to G mod V. And the section just means that, you know, the correct composition is the identity. So the correct composition is, so it just picks from every coset, it just picks an element. Okay, so that's so. And now if you have this, you can define a cocycle. So the cocycle goes from G, so G times G mod V V. It is defined by the following formula. Okay, then I'll draw a picture because the formula is not particularly enlightening. So you start with an element G and the coset H times V. And so what you do is you take S G H V inverse times G times S of H. So now let me draw a picture to explain what is going on. So you have, okay, so I want to define the cocycle from G and H times. Okay, so I have the coset H V, and I have this other coset, which is G H. I also have my my section S. Okay, so S, what it does, it just picks some distinguished point here and some distinguished point here in the coset. Okay. So now what do? I have my G, right? So the G, it sends this coset to this coset. So it sends this element to some point somewhere here. Okay. And now, so what my cocycle does is just correct. So it sends this point here. Okay. So this is what the alpha G H. It's possible it is the other way around. Okay. I'm not completely sure. Because it's always, I mean, you have to write down the formulas and see it exactly. I don't want to do it, but this is what it does. Yeah, so it just corrects for this section to go to the correct point. And so the whole point of this cocycle satisfies the cocycle identity, which is like this. So G1, G2, alpha, G1, times alpha. This is known as the cocycle identity. And once you have something like this, now you can actually write a formula for the section. So let's do it. Now I want to make G act on G mod V times Z. So what do? So I take an element G and I want to make it act so on a coset H V and the point 0. Okay, so what do? On the first coordinate, I just act, G acts on its coset, so I just act in the normal way. So this is G, H, V. And on Z, well, what do? I input, so I have a G and I have AG, so I can apply my cocycle, which is exactly, yeah? So I apply alpha, G, H, V, and remember, so this produces an element of V, right? This was the whole point. So now I can use this cocycle to act on Z. I mean, I can use this element of V to act on Z here. And that's it. And the fact that this satisfies this cocycle identity, actually, I mean, when you write it down, this exactly means that this thing is an action. It's an equivalent. I mean, this thing is an action if and only if the alpha that I started with satisfies the cocycle. Okay. And then the picture that you get is exactly what I did. I mean, you can forget if you haven't seen this before, so you can forget the formulas, but the picture is sort of important to keep in mind that so you can always have a structure.
It's also with S of B to be 1.
Yes, I think that's correct. I think I also want S of B to be 1. Okay. So this is it's a general construction. So for example, this permutation action. I mean, this is one way to obtain it, you start with the trivial action of V on a one-point space. You apply this construction, and of course you get the coset action. Right? Okay, and so now the theorem is that well, this is the only thing that can happen. So for our, of course, very special groups. So let me do it precisely. Okay, so here. Okay, so G is, again, we make our usual assumptions. So G is non-Archimedean relativity compact. And then we start with some arbitrary measured class preserving. This is measured class preserving. And then the conclusion is that there exist open subgroups and PMP actions, so VI, ZI, MUI, so these are PMP, such that, well, you know, the original thing X is just the disjoint union of the induced actions. I didn't introduce notation, but I think it's quite clear. So you induce from VI to G, you induce from this, and we call this sigma I. So basically, this is the only thing that you can do. Okay, of course, you can take this joint union of actions.
Wait, but this induced action, it does not depend on the section you chose.
Oh yes, this I didn't say. It does not depend. This was an important point, which I forgot to say. If you change the section here, you get an action which is isomorphic. Which is easy to see somehow. I mean, the cocycle becomes what is known as a cohomologous cocycle, and then if you have two cocycles which are cohomologous, then the action is somehow the same. And you can correct and get the definition. Okay. All right, so the statement is clear. Of course, I mean, this measure here, I mean, the measure that you get like this is infinite, but it doesn't matter. I mean, so the measure that you get is equivalent to the picture. Okay, so good. So basically, it tells you that, well, so in particular, every measure class preserving action of a group like this is either of type 1 or 2 infinity. Yeah, so this type 3 cannot appear, right? It always preserves either a probability measure or an infinite measure. Of course, a PMP you just get when you take, you know, V equal to G. So this is sort of a silly example. But then in the other cases,
Or finite.
oh yeah, or finite index. That's right. And then in the okay, so let's prove. Actually, the proof is very simple. So that's most of these things. I mean, once you set up things correctly. Okay, so now I'm going to use, however, I mean, all of the theory that I developed last time about this set A and so on. So I'll remind you the whole thing. So right, so you start with the group like this, and then you have this universal permutation action on set U. Universal permutation action. And then you also had this subset A of U, which was somehow, well, it's a section of like to taking algebraic closures and so on. So this is basically the collection of algebraically closed sets, if you want to. It's a universal permutation action of G. So you take all cosets of all open subgroups, for example, something like this. Okay. And then here you just select which have nice properties. So you have this order, which was defined on, say, on A. It's also defined on U, which was that so A is less than B. If so, I always forget. Belongs to algebraic closure. And then what we showed is that this thing on A, this is a lattice, and it is well founded. Okay, so there are no infinite descending chains. And so what was the connection with representations? So if you have now any unitary representation, G H unitary representation, then you can define so for every A, in A you can define this HA, which was just, so you look at O vectors in H, which have finite orbit. Under the stabilizer of A. Okay. So this is a subspace, you take the closure, you get the closed subspace. And so the main point, which again I proved last time, was that if you have now A and B which are in A, then this HA is orthogonal to HB over H of the least upper bound and the greatest lower bound, whatever. Least upper, whatever, this one. I think this is the greatest lower bound. All right, so this is what we did last time. All right, but so okay, now I need something, right? Because if I just have this, it's not particularly useful. So last time we used it for, I mean, these definite actions and so on, and there these spaces were non-empty by definition, right? Because somehow I had, I mean, my Hilbert space was generated by things which, of course, are fixed by the stabilizers, right? If I have some M and I have a random variable which is, you know, it's indexed by A, of course, if I stabilize A, I stabilize the random variable. But here I'm in an abstract situation, right? So I start with just an arbitrary action. So I need some lemma that tells me that, you know, these things are non-empty, because otherwise it's not very useful. I mean, if all of these things are zero, then the whole thing is a bit, it's not logical. Okay, but it turns out that these things, well, they are actually never, I mean, they're never zero. It's not all of them. So there's this like, very simple lemma, which, so again, it's an abstract thing. So you just need the genome Archimedean. Okay, so you can for this. From Archimedean. Well, okay. And then the conclude, well, we have a Hilbert, so we have a unitary representation, continuous, of course. And then the conclusion is that the set of xi in H such that there exists an open subgroup of G which fixes xi is dense. So in particular, there are a lot of things like that, right? I mean, for open subgroups, actually, the set of vectors that are fixed by some open subgroup is dense in the whole space. Okay, so how? I mean, it's a very simple thing to prove. Right, so you start with, I don't know, some eta in H, and we want to find some epsilon. And we want to find something which is close to eta and is fixed by some open subgroup. So what do we do? So we take V small enough such that the diameter of V times eta is less than, well, I don't know, I mean, maybe I want to take eta of 1 or something. It doesn't matter. This is less than epsilon over 10. Of course, I can do this because my action is continuous, and these things, they form a basis at the identity. So of course, if I go to small enough open set, we'll get this. Right? This is a definition of a continuity of the action. Okay, so now what I do, I do the usual trick. So I take the closed convex hull of this set. So the diameter of this, you know, it is still small. I mean, maybe it's less than, I don't know, epsilon over 3. I mean, you cannot, so if you have some set and you take its closed convex hull, the diameter, I'm pretty sure the diameter cannot increase at all, but it can increase, you know, at most 2 times or 5 times. I didn't want to make the calculation, so the diameter, I mean, does not become too big. So in particular, 0 is not inside, right? So 0 is not there.
So can it become bigger? Because it isn't quite get it so.
No, I don't think it can, but it requires some arguments, which I don't want.
This doesn't.
Yeah, this doesn't, because somehow, well, doesn't matter. I mean, so in particular, 0 is not in this thing. And well, so the element of least norm here. So the unique element of minimal norm is fixed. Okay, and it is close. It is fixed. I mean, fixed by V, and it is close to the original.
Doesn't it exist in the first place?
What, this one?
Yeah.
Because the action is continuous. So in particular, yeah, if I have a small neighborhood of the identity, it cannot map at a far away.
Okay, why is 0 not in the convex file?
Well, because the diameter is small, and then at I chose it of normal.
Ah, it's a neighborhood of identity.
Yeah.
In the lemma, then this set is that set you didn't finish writing. I mean, I guess you
The set is this set.
Read it till the end. There exists an open set such that
No.
V times C is
fixed, it's missing.
So
it's
the,
fixed.
oh yes. Well, it is yes. Thank you.
Yeah, thank you.
Yes. Okay. So now we know that all of these things are non-empty. Okay. So this was the point of this. I mean, not all of them, but at least there are some of them which are non-empty, which are non-zero. So now let's. So now we can start the proof here. So choose or the one that I stated about the yes. So the theorem. Oh, I erased it. But it says that if you start with any measure class preserving action of a non-Archimedean relative precompact group, then it's actually it's a union of induced things from PMP actions. So choose a minimal A with H of A. Right, so so this shows that there exists some A for which HA is non-zero. All of the A's were well founded, so there exists a minimum. Okay, so I can take one. So this is where we use this well-foundedness. All right, so now let's take take some F0 maybe HA, and then we remember what the definition of this was. So I mean I can assume that this orbit is finite. Okay, the GA times F0 is some finite. So it's F0.
Which property is this? This minimal A corresponds to maximal.
Yes, not quite. I mean, you have to remember yes, the finite index. Yes, so it will be yes. It is maximal up to finite index. Again, and so this essentially requires some argument to show this is well founded. It is not completely trivial. So that if you just take inclusion of groups, it's obvious that this is well founded. You cannot have an infinite increasing sequence of open subgroups. This is just some relative precompactness. But if every time you're also allowed to take finite index subgroup, then I mean it requires some argument. All right. So this is it's just a finite set like this, and then I can define FA to just be the sum of the absolute values of these things. And so this FA now it is positive, and it is fixed by GA. And because this is the orbit, so of course the sum is fixed. Okay, so now I found the fixed positive vector. So this means this gives me right away. It gives me the support. So E will be the support of. Okay, maybe I should have told you what I'm trying to prove. Right. So we had to prove that this X is the disjoint union of this thing, yeah, VI to GA or to G of some sigma. So this is the goal. So what I'm going to do, I'm just going to find one piece of X which is isomorphic to something like that, and then you can just conclude by Zorn's lemma, right? To take a maximal one, and there can be only countably many because somehow the measure is sigma finite. Okay, so it's just enough to find one piece which is like this, and then you just can exhaust all of them just by taking them one by one. That's what transfinite.
It will actually exhaust.
You do it transfinitely, so you do it, and then you have to stop before omega 1 because somehow the measure is sigma finite. So another option is just use Zorn's lemma directly. So E will be the support of this function fa. And the measure was given as before, so maybe I won't. So, and then there is some mu, which is absolutely continuous with respect to mu, which is fixed by G. So GA times mu is equal to. Okay, and then, I mean, so mu is chosen with random Nicodim derivative, this function, okay? And because it's fixed, so mu is fixed. All right, so now we do have, of course, we do have a measure preserving action of GA on E. So this one is CMP.
FA squared is the derivative.
Maybe there is a square. Okay. So this is a PMP action. So O is good, but now of course also the main point is to show that when I move this E, right? So we have this E, and then my GA, it acts here. But now the whole point is that when I move this set by a G, which is in a different coset, you know, it moves to something, but it does not intersect. And once you do this, then the fact that it is the induced thing just follows from the fact that it's an action. I mean, if you write it down, there is basically no other way to act on these things, which, I mean, you get exactly the same picture which I drew in the beginning. And then you have to believe me that, I mean, this picture can only be obtained in the way which I showed. So there is no more. Okay, so basically the goal now is to, okay, so the goal is to show that, what? That G times E, well, or rather, if you want, G1E intersected G2E is empty if, you know, G1 and G2 belong to different cosets. Which is the same, of course, I can assume that one of them is the identity. By translating, so I can just, so I want to show that GE is empty for G not in G. So this is the goal.
Empty if G not in G.
If. Okay, but so now I basically, I mean, I claim that this follows right away from the. Well, from what we had, right? So what do we have? So remember, we have so that H of A so is orthogonal to H GA over this least upper bound. So now our somehow this is the properties of these A's tells you, I mean, the way that A was selected. I mean, in the first place, I mean, the big A, yeah? That G times A is not in the algebraic closure of A. So in particular, this tells you that this this element, this greatest lower bound, is strictly less than A. I mean, it is normally it's less than or equal, but because you know, the things are not equal, so the lower bound it has to be smaller. Well, but remember the A was chosen in a way that so this is a minimal one such that the thing is non-zero. Well, so this one is smaller, so this one is 0. Okay, so now we just got that these things are orthogonal. But you see, I mean, well, I'm sure I can say now FA is here, and this G times FA is here. So I get two positive functions which are orthogonal to each other, and then you know, their supports have to be disjoint, which is exactly this thing. So there's absolutely nothing happening. I mean, once you set up the things correctly, I mean, you get this. Well, you get this for free. Okay, so I should say maybe that so this theorem actually was proved. So this was proved by Nesonov infinity, okay, using sort of similar techniques from representation here. But then, okay, so to do it for all oligomorphic groups, you have to know these these algebraic closures and so on for this to work. Okay. All right, so are there questions about this? Okay, so the upshot of this is that there are no interesting measure class preserving actions for these groups. So you can as well just study PMP actions, of which there are many interesting ones. So I'm maybe going to show you like in the remaining 10 or 15 minutes some more examples of things that you can. So far so good. All right. Okay. Yeah, okay, so maybe I'll just try to state maybe one more theorem. To show what things you can do with say with this definitive thing, which then last time. So Coulomb. So he also, in his work with Mathieu Joseph, they found some other applications which are very nice, and so this is something older that is in the paper of Coulomb and me. It's about the actions on linear orders. Okay, so that's the definition. So you have let me see. So you have G, maybe so the automorphism group of M, where M is some structure, and then so you get there's this space of linear orders on M. Okay, so this is the space of all x in 2 to the n squared, such that x is a linear order. It's a relation, right? It's a relation on two letters, and so being a linear order is, it's a closed, it's a closed condition. So this is a compact. And then of course, so you act for your group G. It acts just by shift. So the action is that down, so A less in the order G times X than P, if and only if. Okay. So this is the definition of the action. Okay, then so there is let me see. So there's a reason to consider this. There's not, of course, just some action on some complex space. But for example, when you take G, say to be the full symmetric group, then so it is a theorem. So it's a theorem of Glasser and Weiss that the linear orders actually what is known as the universal minimum flow. Okay, so it is so the action is minimal. So maybe this I can show you right away. But what is the important part is sort of the universal minimal action for this group, and then it's also the universal minimal action for many other groups. I'll maybe give you some list or something, and then I'll explain later. Okay, so let's see. So why this action minimal? So if you have this is easy to see. So if you have some x in some linear order, and then you have some open set. So with an open set, right? It's the product topology. So an open set is just given that you take k elements and then you decide how you order. Right? So this is an open set, and this is the point x. X maybe orders them in some different way, but you have all possible permutations. So you can just permute these elements to be ordered in the correct way. So this will send the point x in this open set. So that's all. Okay, so it's a bit silly. It's very easy to check that this action. Right, so this is a minimal action. And so another thing that Glasner and Weiss noticed is that so this thing has, I mean, there is an invariant measure, and it is unique. Okay, so let me. So there are several ways to find the measure. So one way is just to just say that so the measure of a set like this is k factorial. The thing is that you don't have any other choice, right? I mean, the thing is that because the measure is invariant under this, and then we look at all permutations of these k things. I mean, you get disjoint sets, and then there are elements of the group sending each one to each of the others, so they had better have the same measure. Okay, so this is the only thing that you can have. And then you check that this actually defines a measure. Okay, I mean, there's something to check, of course, that when you just declare the measures to be like this, it adds up. When you add a k plus first point, you have to check that the measure is actually adds up together, but it does. But there is a way which I like better of defining this measure, and which is somehow relevant. This also shows that the measure is unique. Yeah? What I just told you, that I mean, if there is an invariant measure, it must satisfy this. So there is a slightly different way to do this. We have like this. So we have this omega here. That's okay. So here we have just 0, 1. So this is the interval 0, 1 to the power n. And then I want to look at the subset of it. So omega is just the set of all injective sequences. So this is OZ in 0, 1. And such that for all A different from B, Z of A. So here I also put, well, here I have my canonical measures. I say take Lebesgue measure on 0, 1, and then just take the
injections of M into 0.
Yes, injections of M into 0, 1. And then so the measure that I have here is, so it is lambda to the power m. So again, so I just have, if you want, random variables indexed by m, which are all independent and are uniformly distributed on 0. Okay, and then of course this omega has measure 1. Of course, almost every sequence that I choose, I mean, the probability that things are equal is 0. Okay, so now I have a map that goes from here to here. So what is the map? I have the map is very simple, right? I have my sequence of like elements of 0, 1 indexed by m. But this thing, it's ordered, right? It's an interval. So I can just look at the order and then restrict the order to m and then get an order on m. And this is obvious. So this procedure, it gives an invariant linear order on m. Okay. So maybe should I write it down? So pi f, right? Sorry. Won't like this. So A is less in the order pi of z than B, if and only if well, z of A is less than z of B. That is 1 to z is no.
It doesn't give invariant order, gives invariant measure.
Sorry, yes, it gives an invariant random order, invariant measure set of orders. And somehow it doesn't really matter with what measure you start here, as long as it has no atoms, so that this omega actually is, it has measure 1, then you're okay. You still get the same. And so now the whole point of this business is that, okay, so this measure for S infinity, I mean, it exists, it is unique, and so on. But somehow, even for a lot smaller groups, this is still the unique invariant measure. Okay, so this was considered by Angel, Claude, and Lyon. Say something. So Angel, Lyon, so they considered, well, what they really considered is the action of automorphism group of, well, some structure on its universal minimal flow. And then they asked this question, which is the question. So if this thing is amenable just means that every action on a compact space has an invariant measure. Okay, every continuous action on a compact space. Then is it true? Well, and this is metrizable. Okay, and your math M is metrizable. Does this imply that there is a unique invariant measure? What is what?
UMF.
The universal minimal flow, which I'm not going to define for lack of time. So there is a unique invariant measure. Of G. Sorry. Okay. And so the whole, I mean, the reason that look at these linear orders is actually the linear orders are somehow, well, very intimately connected. I mean, at least in the cases where people can calculate these universal minimal flows. So for many groups, they're either equal to the linear orders of the structure, or maybe it's a subset of it, or they're related in some other way. So, I mean, examples, if you want, is that if you look, say, at the automorphism group of the random graph, of K and free graphs, what else? I don't know, there is a long list of things. I mean, if you just want things, so for these, the universal
Hypergraphs.
hypergraphs, yes, thanks. Again, so these universal hypergraphs and or intermediate configurations and so on. So in all of these cases, the universal minimal flow is actually equal to the linear orders on the structure. And then in many other cases, you get a subset. I mean, for example, I don't know, if you look at say vector spaces or Boolean algebras or things like this, then you get actually a subset of this. Okay. And so what Angel Kekris and Lyons they did, okay, they asked this question. I mean, it was motivated by their results. Okay, the results is that in basically all of the cases that they could calculate, this thing was uniquely ergodic. Okay, so this measure, I mean, this measure that we have, which is invariant in the rest infinity, was actually the only measure which was invariant even under these smaller groups. Okay, so we can't really say anything about this, the universal minimal flow, as an abstract object. So this is hard, as far as I know. I mean, there are no results about this, but you can say something about this, which is more concrete. And so it turns out that this is, I mean, this is sort of a pretty general phenomenon. The uniqueness. So here is the result, which again, so it uses all of this business. So you get the Finetti's theorem, and so on. So this is result with Coulomb. So what is it? That okay, now we have to make the list of all the assumptions. So now we have the strong list of assumptions, so that the Finetti thing holds. Right, so M is Aleph 0 categorical. It's transitive. Something. So trivial algebraic closure and with termination of the measure. Okay. So this was the strong list of assumptions which told us what this set A was, and then you get to get definite. I mean, really, the thing that is used is this definite. Okay, and then the conclusion is, so you look at this group, the action on the linear orders, and the conclusion is that this is uniquely ergodic. So basically, the only invariant measure is this.
No, that's not true.
Probably. Why is it not true?
It's uniquely ergodic or there is a fixed point.
Oh, thank you. Sorry about that. There is a fixed point. Yeah, I know. Right. I mean, if you have, of course, if there is there's a fixed point, there's a fixed point. So this measure is always invariant, and then you can somehow combine, if you want, the fixed point. Yes. Okay. Maybe I'll say one last thing, and then I'll stop. So, for example, I mean, this gives a bit of a funny corollaries, because you see, I mean, here there's no assumption of minimality of this action. So, for example, what you get is that, say, if the automorphism group of M is amenable, then this action has to be minimal. What? Minimal, right? Because you see, if the action is not minimal, well, then there is a subset which is invariant, and then if the if the group is amenable, this subset, it must carry an invariant measure. But somehow it cannot, because the only invariant measure is this big one, which is concentrated on the whole thing. So you can recover things. For example, I mean, there's a theorem of Kekris and Sokic, which says that if you look at the automorphism group of this partial order, how is it called? The universal homogeneous partial order, then this action is not minimal, because you can look at all orders which extend the given partial order. And then you can apply this theorem and get the group is not amenable, which of course they check. I mean, you can just also directly check that the action on this thing does not have an invariant measure. But again, so this puts it, if you want, in some sort of more general framework. But okay, so this only works for this particular action. Okay, it's an important action for groups. I mean, for these groups on linear orders, but somehow it only works for linear orders. It does not work for arbitrary. So I think I'll stop here.
Other further questions?
So probably a silly question, but what if M is Q, then what is the conclusion here?
That's a fixed point. Because the Q is, I mean, this is why you need the C.
But there's no, it's not unique there, good.
No, it is not, because you have the fixed point and you have this measure. So for Q, for example, you can actually describe all measures. They do come from, there's ways to combine the fixed point and, I mean, they're more ergodic measures, but they can all be described in terms of the fixed point and the big one. But somehow in general, well, so when he tried to do this, it was not so clear.
No, but for Q, it's also that the UMF is just a point. So it's uniquely ergodic, like it falls in this question, but for severe reasons.
Yeah, I mean, this question is still it's very widely open. I mean, the reason is that, well, first of all, I mean, no one, I don't know whether it's true or not, but somehow people just do it when you have a concrete calculation, okay, and then you can check. I mean, you have a concrete action, and then it's not necessarily easy to check. I mean, Andrew Kekris and Lattice, even for each of these particular cases, they actually use quite a lot of probability theory and whatnot to calculate to check that the thing is uniquely ergodic. But somehow, if you don't know what the UMF is, there are no methods. I mean, just abstractly from meterizability to conclude unique ergodicity.
Without meterizability, there are counterexamples. Other counterexamples when it's not meterized.
Oh yes, of course. So if you have any countable amenable group, this is like very false. And this was even locally compact. So this was shown again by Kurna and Andy.
Non-compact.
Non-compact, yes. So if you have any locally compact, non-compact group, so Kurna and Andy Zucker, they showed that this thing just never holds. There are a lot of invariant measures.
Further questions? Let's thank the speaker again for a feedback.